My name is Professor Karina Hjelmevik, and I would like to present our study on drift patterns of plastic emissions in coastal areas. Tiny plastic pellets are the pre-production building blocks of nearly all plastic goods. Unfortunately, they become an environmental hazard if lost during transit. The pellets are also mistaken for food by seabirds, fish, and mammals. Removal of plastic pellets from the beaches is a tedious process. One of these gentlemen uses his hand to look through the sand and locate the pellets, and the other a sort of vacuum cleaner to gather them. Such pellets are found on many beaches all around the globe. I would like to take you to Norway and the Oslofjorden. The Oslofjord is located in the southern part of Norway, with the capital Oslo in the innermost part of the fjord. Recently, 13 tons of plastic pellets were lost during transit and is now polluting our coastline. A container vessel encountered harsh weather during transit from Germany to the western part of Norway in February. About a month later, the pellets were observed in the Oslofjord. Investigation showed that the pellets stemmed from the container vessel. In May, we were contacted by the coastal administration. More pellets than they expected had entered the fjord, and they needed predictions on where to find the pellets along the 5,500 kilometers of coastline in the fjord. During the last few years, we have been working on the ocean model Fjordos to predict currents and hydrography in the fjord. Modeling of drift patterns in coastal areas is a challenging task due to complex topography causing a flow pattern that varies over short distances and during short periods in time. In a numerical model, we try to mimic reality through equations. In order to give predictions of the drift patterns, we need to know the flow pattern. The Oslofjord has a complex topography with shallow areas, narrow straits, and islands. Since the currents are sensitive to the topography, you need an accurate bathymetry. We wanted to use the regional ocean model system, also called ROMS, and divided the water column into 42 depth-following layers. The tidal elevation is only around half a meter, but the tidal currents can be up to 4 meters per second in the more narrow straits. In the south, we need to know the boundary forcing from the surrounding ocean. Due to several rivers, there is a mix of fresh and salt water in the fjord, which is rather typical for coastal waters. Finally, the current and hydrography depend on the atmospheric forcing, including wind, rain, heating, and pressure variations. The result is rather complex currents with daily variations, seasonal variations, and depth variations. Here we show an example of sea surface temperature. You can see the cold water from the ocean entering the fjord in the south. In the eastern branch, the water is heated during the day and cooled off during the nighttime. But due to a large river in the western branch, that heating is less profound. Close to the city of Fredrikstad in the southeast, another large river with cold water enters the fjord. The mix of fresh and more saline water has an impact on the flow pattern. You can also notice the tides with a cycle of 12 hours. In addition to the daily variations, we have seasonal variations and also depth variations. The drift patterns depend both on currents and on wind, especially for items such as plastic pellets, which floats in the surface. So we used our ocean model together with an atmospheric model in a Lagrangian drift model. We chose a drift model called Open Drift, which is an open source model that we have relatively good experience with. So back to our situation with the plastic pellets. By May, the pellets had washed on and off the beaches and were pretty much everywhere in the fjord, and still more was entering the fjord. Let's say some pellets enter the fjord in the position marked by the red square at noon the 5th of May. The drift model predicts that they will strand outside of a city named Moss, along the eastern side of the fjord. So should we send all our personnel and material to clean that specific beach? Unfortunately, it's not that simple. These are the expected stranding points of particles released at the same position but during a time span of 24 hours, according to the drift model. Many of the pellets are expected to strand close to the city of Moss, but not all, as the trajectories are sensitive to the currents which change with time. And these are the expected stranding points of particles released at the same time but with slightly different starting positions, again according to the drift model. And again, many of the pellets are expected to strand close to the city of Moss, but not all, as the trajectories are sensitive to the currents, which also changes with position. In addition, we do not know where the pellets enter the fjord. They are pretty much impossible to spot at sea. Here are the calculated trajectories of particles that enter the fjord at the same time. So tracking every single particle is pretty much impossible. Instead, we have to make statistics to identify the most probable drift patterns and hotspots where the pellets were most likely to be washed up on land. Therefore, we chose approximately 6,700 positions close to the southern boundary of the fjord. And then we calculated trajectories for particles released every hour from 1st of April to 15th of May in each of these positions. The result was more than 300,000 different trajectories. So here is a snapshot of the most probable drift patterns. Of course, the concentration of particles were high in the area of the starting points, but as you can see, more pellets choose to follow the eastern coastline, and some areas are left more or less untouched. And here is the most likely hotspots where the pellets are expected to accumulate on land. As you can see, the concentration of pellets are expected to be higher along the eastern side of the fjord, and no pellets are expected in the western branch. In the northern end of the western branch is a relatively large river which creates a south-going surface current of brackish water and thereby prevents the pellets from moving northwards. For obvious reasons, the concentrations are expected to be high close to the area where the pellets are released. As a part of the process, the coastal administration created a map where the observations are marked. The map also shows which areas have been cleaned. There seemed to be a nice compliance between our model hotspots and where the pellets have actually been observed. The quality of the observation varies. Sometimes the pellets were of a different type, and sometimes the pellets were washed off land before further investigations. After manually filtering the observations, we compared with the predictions. The true positive positions are marked with cyan, that is, positions with observations where the model predicts beach pellets. The true negative positions are marked with red. That is, positions with observations, but the model did not predict beach pellets. And the false positive positions are marked with blue. That is, positions without observations, but the model predicts a possibility of beach pellets. Please note that not all pellets are located, and that a position without observations does not state that no pellets are present in that position. The plot only shows where observations are made and not the amount of pellets. Large amounts of pellets were gathered in areas close to the city of Moss and east of the city of Fredrikstad. If you compare with the predictions, you see that the probability of beach pellets are high outside of Moss at the exact same position. East of Fredrikstad, the model seemed to fail. A closer look reveals that the model predicts a relatively high concentration of pellets in the same area, but not in the exact same positions where the pellets were actually observed. Please note that the coastline is divided into line segments with a length of 100 to 400 meters, which is a pretty strict requirement. Longer line segments would result in seemingly a better match. The confusion metrics show that only a few positions are true negative and that the model captures most of the observations. But again, longer line segments would result in seemingly better results, but would be less applicable for cleanup operations. In this case, we divided the coastline into almost 8,000 line segments. So, what have we learned? Well, we already knew that the drift patterns in coastal areas are sensitive to challenging flow patterns in coastal areas. But through this study, we got that further confirmed. And we realized that producing statistical plots made more sense than one single outcome. To capture the local phenomena, we need a model with high resolution. There is a high degree of compliance with observations, and that encouraged us to recommend this method for other studies and applications. Thank you for listening.